Hello there. In this video we're going to be discussing cumulative distribution functions for random variables, both discrete and also continuous. So let x be a discrete random variable x with probability mass function p and support s. Remember, the support of a probability mass function is the set of all values x such that p is not equal to 0. Then the cumulative distribution functions, or for short CDF, of x is given by the sum from k is equal to the minimum of the support to x of px of k. We're going to be going through examples for both discrete and continuous random variables for this. Alright, so the first thing we want to do is get comfortable with this notation and this definition. So what I'm going to do is I'm going to create a tabular PMF with x values 1, 2, and 3 with probability values 0.3, 0.4, and 0.3. And we're going to be calculating the CDF values of capital F of x. So if x is equal to 1, then we're going to be defining the cumulative distribution function to be equal to whatever that probability value is. Because the probability cumulative function starts off at the minimum value, which is x in this case, and adds up all the probabilities starting from that point up to whatever value we're interested in. In this case, we're interested in 1, so we only need to add up 1. So for x is equal to 2, this is going to be equal to the sum of the probability at 1 and 2. So that's going to be 0.3 plus 0.4, which is going to be equal to 0.7. And then for x is equal to 3, what we want to do is add up the probabilities at 3 and everything before it. So 3, 4, 5, right? So that's going to be 0.7 plus 0.3, which is 1.0, right? So we have that. Notice that we do not need to add up vertically for each of these things. We can just take 0.3 plus 0.4 to get 0.7 and 0.7 plus 0.3 to get 1.0. Like that's a quicker way to do it if you're doing it by hand. So this is the cumulative distribution function, or CDF. And it pretty much tells you the up to some point, what is the total probability that x is less than or equal to that value. So now let's do a more intrinsic example, or complicated example, I guess you could call it. So let us suppose that x is geometric with parameter p. So remember, geometric random variables are random variables that measure the number of trials until the first success occurs, right? So you need at least one, right? So if x is geometric, that means the support of the probability mass function p of x is going to be equal to 1, 2, 3, 4, and so on, right? All right, cool. So now let us calculate the probability, or the cumulative probability distribution function for geometric random variable, which by definition is the sum from k is equal to the minimum of the support, which in this case is 1, up to whatever value of x that we're interested in, right? So this is going to be equal to, by definition, px of 1 plus px of 2 plus px of 3 plus all the way up to px of whatever number we're interested in, say x. So when x is equal to 1, then that's just going to be equal to p, namely 1 success. So we try, get we first success. That means we haven't failed if we only try once. So when x is equal to 2, that means we have 1 failure, 1 success. When x is equal to 3, we have 2 failures, 1 success, all the way up to, for x is equal to x, that means we have 1 minus x minus 1 failures and 1 success, right? So I can clearly factor out a p here, right? So I have p multiplied by 1 plus 1 minus p plus 1 minus p, the quantity squared, plus all the way up to 1 minus p to the power x minus 1, right? So remember, I can rewrite this as 1 minus p to the power of 0, and I'm going to be replacing x minus 1 with n, right? So that means this is just the same thing as saying p times the sum from k is equal to 0 to the power of n of 1 minus p to the power of k. Right? Now I'm going to replace 1 minus p. I'm going to define this. So 1 minus p, I'm going to define that to be equal to y. So if I do that, then we have p multiplied by the sum from k is equal to 0 to n of y to the power of k. Now we should be able to notice that this is a finite sum and of course has a closed form if you remember from pre-calculus. If you remember, this is going to be equal to y to the m plus 1 minus 1 all over y minus 1. Okay, cool. So n is by definition x minus 1, and y by definition is 1 minus p. So let's just replace these back in here now that we know and can recognize that expression. So this is going to be equal to p times 1 minus p. Then we have x minus 1 plus 1 minus 1 all over 1 minus p minus 1. We clearly see some 1's cancel out. That's great. And also, p's cancel. Now keep in mind there is still this negative sign there, so don't forget that. So I'm just going to distribute that in the top, and that's going to give us 1 minus the quantity 1 minus p to the power of x. Why just x? Because 1 negative 1 cancel. Right? Therefore, the cumulative density or probability function for geometric random variable is going to be equal to 1 minus p to the power of x. So this is for geometric x. Alright, so let's do a practical example of how you may want to use cumulative distribution functions. So let us assume that x is geometric with the probability of success being equal to 40%. And let us assume we're interested in the probability that we get our first success in the first 7 trials. So of course this is the same or equivalent to writing the probability that x is in between 1 and 7. So remember, this by definition is the cumulative distribution function evaluated at 7. So this is equal to fx of 7. So instead of doing each of those individual probabilities, we can just plug in 7 into the CDF and get our answer directly. So this is going to be equal to 1 minus the probability of success to the power of 7, which is equal to 1 minus 0.6 to the power of 7. And you can find that this is approximately equal to 0.972, or about a 97.2% chance of occurring. Now, one property that you should know for CDFs, for discrete random variables, is as you approach infinity for the cumulative distribution function, this should be equal to 1, assuming that the support for x is not bounded above, right? Or if the support of the probability mass function is, say, 1, 2, 3, 4, up to some number, say b, then fx of b is going to be equal to 1, because that's the sum of all of the values, the probabilities 1, 2, 3, 4 up to b, and since p is a probability mass function, the sum of all of its probabilities must be equal to 1. So that's pretty much what this expression means. Right. So now let us take a look at the continuous case. So now let us suppose that x is a continuous random variable with probability density function, let's call it f, with support gamma. Right? Then the CDF of x is given by the following. So capital F of x, same notation. So this is going to be equal to the integral from the minimum of the support to some value x of our probability density function, which is usually denoted by fx of t dt. Alright, so the first example that we're going to be looking at for the continuous case is a uniform random variable on some general interval a comma b. So remember that this is the probability density function for a uniform random variable. So let's also calculate the general CDF for a uniform random variable as well. So that means fx of x, by definition, is going to be equal to the integral from the minimum of our interval, which in this case is a, up to whatever value we're interested in x, of the constant. So 1 over b minus a is just a constant, so the integration of that is no big deal. So we have 1 over b minus a times t, evaluated as t goes to x and as t goes to a. So therefore, the general CDF for a uniform random variable is going to be equal to x minus a over b minus a. It's very easy to prove as a direct corollary of that the CDF evaluated at b of a uniform random variable is just going to be equal to 1. So now let us take a look at another continuous random variable that is also should be familiar to us. So let x be exponential with parameter lambda. Therefore, the density function for x, as we should know, is going to be equal to lambda e to the minus lambda x when x is greater than or equal to 0, and 0 for x less than 0. Remember that this is equivalent to another form, 1 over beta e to the minus 1 over beta x for x greater than or equal to 0, and 0 for x less than 0, where the connection between these constants is lambda is going to be equal to 1 over beta. Different context, different meaning. Right. So I'm going to be working with this one since I don't want to deal with fractions. So capital F of x is going to be equal to the integral from the minimum of our support, which is going to be 0, up to x of lambda e to the minus lambda t dt. Alright, so lambda is a constant, so I can factor it out, and then I can divide by negative lambda by the fundamental theorem of calculus. So I have lambda times minus 1 over lambda times e to the minus lambda t, evaluated as t goes to x and as t goes to 0. Alright, as we see, these lambdas will cancel, and we have a negative coefficient outside. So we have minus, so we have e to the minus lambda x minus e to the lambda 0, which is just 1. And once we negate that, we have the general cumulative distribution function, 1 minus e to the minus lambda x. So if somebody asks you, what is the probability that x is less than or equal to, say, 5 hours, assuming that lambda is equal to 3 hours for, I don't know, exercising per day. So the average of exercise is 3 hours every day. What is the probability that you spend less than 5 hours for that? So if we assume that x is exponential, then we can use this result that we just derived directly. So remember that if x is exponential, the minimum of the support is going to be equal to 0. So this is equivalent to saying the probability that 0 is less than or equal to x is less than or equal to 5, which by definition is the value of the CDF evaluated at 5. So using our CDF result that we just got, that's going to be equal to 1 minus e to the power negative 5 times 3, which is going to be equal to 1 minus e to the power negative 15. So as we know, e to the minus 15 is close to 0, therefore this result is going to be close to 1. Therefore, if on average you spend 3 hours and the amount of exercise time you spend every day is exponentially distributed, then it's almost certain that you will spend less than or equal to 5 hours every day. Anyway, that's some examples and derivations on how to calculate and use the CDF of discrete and continuous random variables. Hope you enjoyed.